All right. You're gonna like this one because it's a well, you may not like it, I don't know, but it's a formula slash rule, and you can honestly apply it mindlessly. Um, and if you want to think about what it means, it's not even that hard to think and consider intuitively what it means. Here's the idea, and this may seem like a strange idea until you see some examples, particularly say in physics or in engineering. So right now, the only downside of this is you probably should wonder, why am I doing this? But if you'll just suspend that thought for a minute, see if I can grab always grabbing for a better marker. All right. So the idea is here, suppose we have a function, which is a function of, say, two variables, and it is whatever it is. I can make up some rule over here, but let's just say that equals z. But then you find out that x and y themselves are a function of some other variable. So let's suppose that x is a function of t. Well, how should we write this? We might want to write it something like, okay, so x is equal to, we can write a bunch of different ways, say f of t and y is equal to g of t. Is that visible on the board? I'm not sure. Hold on. I'm going to rewrite that. Okay, let's write it over here. Let's suppose that it turns out that x is a function of t and y is a function of t. I use t because, say, in physics, you might think of t as time. And x and y, maybe this is temperature and this is volume, and maybe this determines pressure. So although the pressure is a function of, I don't know what I just said, temperature and volume themselves may be changing over time. So that's the sort of situation in which you could have something like this. Now, what we want to do is to find dz dt. I stumbled there for a second because I was thinking I could have said f prime. I could have said df dt. I could have written the f with a little t down here. Now, this is a function of two variables, but each of those variables is a function of one variable. So, if you know t, you know z. And that means that f ultimately is a function of one variable. And so this expression right here makes sense. This makes sense. And it turns out that, well, here's the rule for it. We do this. We do the partial of f with respect to x times the derivative of x with respect to t plus the partial of f with respect to y times, sorry about that, dt and dt. Now, what's the intuitive idea what's going on here? The idea is this, the expression I'm covering up right now, that gives us a rate of change. Rate of change of what? Rate of change of f with respect to x. But x itself is changing as t changes. So this is the rate of the change of x. So what you have here really is a chain rule, or it's a version of the chain rule. And if I restrict my attention away from y, forget about y doesn't exist, y is a constant, then I would write df, dx, dx, dt. And this would be the standard regular chain rule. Same thing over here. So another way to look at it, this is giving me the change, although it's a change in terms of t, but it's the change induced by the change in x. And this is the change in z induced by the change in y, which is changing as t changes. Okay, and so this is just, we add up those two changes to get the overall total change. Now here's the great part of it is what kind of a question. I'm not going to ask you to prove this. Hey, real quick thing. I heard somebody say somewhere along the way that you could prove this in a completely bogus, false way, but nonetheless it feels oddly satisfying. You can't cancel out this with this. These aren't fractions, but let's just pretend you could for a minute. Cancel that out and cancel that out. And then you see where you head with that. It would actually change the function back into a function of one variable. Now, hey, one quick thing. Well, here, let me write down an example. And as soon as I write down the example, you should raise your hand and say, hey, but wait a minute, why don't we? So here's an example function. Let's say we had f of x comma y, say equal x squared times y plus y cosine of x. And suppose furthermore that x of t is equal to the square root of t, and y of t is equal to the natural logarithm of t. And the question would read something like, find df dt. Okay, I'm going to use this rule. Right now you should say, but, and what you should say is, why don't we just take this, plug it in here, we'll have a regular old-timey function of one variable, and we're right back in Calc 1, and we do this. So you're just going to have to hold on to that question for right now, because you kind of should wonder that. Oh, could we do that? Absolutely. Will we get the same answer? We better get the same answer, or something's wrong with our mathematics. Now, what does this tell you? This is really just another formula, and it tells you the pieces you need to construct. So in no particular order, I don't know, let's find df, or the partial of f with respect to x. We look at where's the function? Right here. It's the partial with respect to x, so we look at y as a constant. So this is 2yx, plus, remember, not a product rule, right? Because y is just a constant. Y is a constant, so the derivative of that will wind up being minus y sine of x. And let's find the partial of f with respect to y. Again, this is no particular order, but with respect to y, so this is a constant. So the derivative there is x squared. And with respect to y, so that's a constant. So we get, oh, not too bad. Okay, plus, although it hardly matters here. Because once we get this all calculated, that's it. Problem done for right now. We need to find dx dt. Dx dt, where is x? Right here. So that's what, 1 over the square root of t. That's just standard old Calc 1 stuff, right? And dy dt is 1 over t. And so now we just put everything together via this formula right here. If I had been a little wiser, I would have left a little more room here. Let's see if I can go ahead and put it in here anyway. So dz dt is equal to this piece of the puzzle, 2yx minus y sine of x. And dx dt, where's the piece there? 1 over the square root of t plus df dy, where's that right here? X squared plus cosine x times dy dt, 1 over t. And, we should simplify this like, wait a minute, something feels very, very unsatisfactory there, which is not wrong, but feels very, very unsatisfactory. What feels unsatisfactory? Here I've got this equation, now I've got as a function of 3 variables. And I think at this point, without a doubt, hey, to make our lives easier, maybe I could have said something like this. Find this evaluated at a particular time. That would be nice. In fact, can I guarantee to you that I will do it that way on the test? Not I can't guarantee because I don't know what I'll be thinking when I make up the test. But, at this point right here, you either want to substitute these two functions in for x and y here, then you'll have everything as a function of t. Or you could solve this for t, and you could solve this for t, right? I mean, you know what I mean, right? So here t would equal x squared, and t would equal e to the y. And then you would put that in for t here. So what would we have here? T x squared. You'd put x squared, so that would be 1 over x. And then 1 over t, so this would be, maybe e to the negative y. You could do it that way if you wanted to. But more likely, the standard sort of question here is you would be asked to determine this when, now I could either have said when x is at a certain value, x and y is a certain value, or t is a certain value. Let's just say t is, I gotta make sure it's in the domain too, right? I wouldn't want to make t equal to 0, because you could do that. I mean, should we make life really, really easy and make t equal to 1? I don't know. I don't know if that makes life too easy or not. But if I make t equal to 1, what's the natural logarithm of 1? Right there. 0, so that makes y equal to 0. And if I make t1, that makes x equal to 1. And then we would just come on over here. I don't need that anymore. Let's erase this. So I could have said this evaluated when t equals 1. So dz dt evaluated when t equals 1. We know what all the components are here. Y was 0, right? So that goes away. That does that make things too easy? I don't know. But at any rate, it's still a valid problem. And what do we have over here? We have 1 plus cosine of 1. So 1 plus cosine of 1 times, what was t? T was 1. So there it is. 1 plus cosine of 1. Hey, that's kind of nice. That's easy. Okay, so this is a chain rule for multivariable functions. And, I think it's maybe you guess, and it's true, you could extend this for functions of more than 2 variables. Right, you'd have df dx, df dt, df, well, I have a poltergeist in the room, df dy, dy dt, and you could have plus df d, say you had a third variable, dz dt, etc., etc. This is all I'm really concerned with here. All right. Oh, yeah, sorry, before I sign off here. One way you could look at this, and I think you should try looking at it this way, is the following. T changes, and I imagine as t changes here, x and y are functions of t. As t changes, as you roll along the x-axis, what is the x-axis? Well, it's a straight line. Well, as I go along that straight line, each value of t I plug in here gives me a coordinate, an ordered pair in the xy plane. And so what would you be doing? You would be following a curve, a one-dimensional curve in the xy plane. And then this would be a curve on the surface of the graph. So one underlying thing that's going on here is we have the surface of a graph. Right, maybe, I don't know, here's the surface, right? That's supposed to be look, it's not supposed to have any thickness, okay? But it's a surface. And you have the real number line, and the real number line maps to some, this is supposed to be the xy plane down here. It maps to some curve in the xy plane. So here's the xy plane, whee, and we go along this curve right here. Up above here, we're following a curve, along the surface. And this derivative is giving us the slope as we go along that curve. It would be better to say rate of change than slope, because slope we'd have to think, what the heck does it mean? Because after all, once we're up here, we're in 3 dimensions. So let's just leave it as rate of change. Although we could make some sense out of slope. Maybe you think about how to make some sense out of slope. In fact, go back to the TNB coordinate framework concept, where we have that coordinate at every new coordinate system at every point in space. And you might want to consider what that means, but we don't need to worry about that right now. But you might want to think about it anyway. Okay, so there's the formula. There's the calculation. Easy and the exam. All right, more videos coming up.